or all such varied cases in that single framework. Then other cases, if you see, then this is the division corresponding to that restricted feedback case. For a full feedback case for a MIMO system, this is the key gain value corresponding to there are 4 outputs and 2 inputs, 2 by 4 matrix, right? 4 outputs and 2 inputs to the plant. And this is a full matrix in the sense all the values or all the elements of this key matrix are not restricted. You can design them and take any arbitrary value based on your choice. But if you see the restricted feedback case, often in many applications we try to see or try to design a controller where some of the input to output to input connection are set at 0, that we don't connect from this output to input. Induction motor vector control is also a similar problem, that some of the outputs are restricted to get connected to the input side through a gain. So then we put these terms. For example, for this case, the off-diagonal terms for the upper triangular and for the upper diagonal and the lower diagonal, all these terms are 0. There are no connection. That does mean this is 4 by 4. There are 4 outputs and 4 inputs, and only the first output is used for constructing the first input, second output for the second input, and that one. And there could be variation of this as well. For those cases, we may see this is a tri-diagonal structure, that it takes neighboring output information, that the first one or first input is constructed using the first output and the second output. The third and fourth outputs are not connected, right, to the first input. And that way you can restrict based on your application. For example, in multi-agent system, you will see that one agent uses neighboring information. So in that case, you will find a tri-diagonal structure of the controller and have to design the controller so that the control gain will be in such restricted format. And once you have designed, then you can apply that to your particular application. And obviously, we'll discuss for this induction motor applications, not only the static output feedback, but also this structural restriction, or when structural restriction have been added to the controller gain, that these gains are not or should be kept at 0 value. So that thing we'll also discuss. So for that, we'll briefly introduce or go through the linear matrix inequalities. Linear matrix inequalities, it's a tool using which we can solve such problems more easily, and many control design problems can be framed as an LMI problem to get a numerical solution for the design. So let us look at what a linear matrix inequality is. A linear matrix inequality is an expression of the form this. In this fx, this left hand side, this one is equal to summation of f0 plus x1 f1 plus up to xn fn. This is less than 0. Less than 0 means the left hand side is negative definite matrix. Negative definite in the sense, obviously it should satisfy the symmetricness and all this. Again, this f0 f1 up to fn, these are known matrices, and x1 up to xn, these are the variables and we have to solve. So such problems, or when such constraints are involved in an optimization problem, then we call them as linear matrix inequality. Many problems in control theory that appear as an LMI problem. For example, the Lyapunov inequality, if you remember that for determining whether a system is stable either in continuous time or discrete time, that appears as an LMI problem, that you have to find a x greater than 0, which is positive definite, satisfying this A transpose x plus x A transpose, this is less than 0. Okay. Similarly, for discrete time case, you will find that this is also an LMI problem. You have to find a positive definite x satisfying this constraint. So for matrix case, obviously, if we can visualize this more easily using problem. Consider this inequality y greater than 0 and y minus x squared greater than 0. You have to find x and y satisfying these two inequalities. Y and x are scalar here. The second one, the second inequality y minus x squared greater than 0, that can be expressed as this, that this is greater than 0. If you can ensure that this y x x1 this is greater than 0, then if you take the determinant of this matrix, then that is equal to y minus x squared greater than 0, and that comes as property of this inequality that its determinant also has to be greater than 0. So that way, even if many of the inequalities that look like not in that form or LMI form, but still you can use tools or their properties to express them as LMIs. So if we look at this greater than 0, then we can write this one 0, 0, 0, 1 plus y is a decision variable into 1, 0, 0, 0, and x is another decision variable multiplied by this summation should be greater than 0, and x, y are the decision variables. So you can see this one is expressed as this, which is in similar fashion as we have written here in the previous slide, right? So even if nowadays parsers are available, in the sense if you write the inequality in this form, it will parse out or break the inequality in this particular form, in that LMI form, and tools are also available using which you can easily solve these problems. One of the toolbox is that LMI control toolbox of MATLAB. Other MATLAB based packages also available, and in that you can solve several sort of problems that appear for solving a control region problem. In general, these three optimization problems are embedded in this toolbox. Optimization problem solvers. First one is that the feasibility problem that finds whether a solution exists for such an inequality. The second one is that linear objective minimization problem, that given such matrix inequalities, if you can minimize certain objectives that are combinations of the decision variables. And generalized eigenvalue minimization problem. I will give an example how easy it is to solve using these solvers or calling out these solvers. The solvers are that FISB means CX and GEVP corresponding to these three problems. Okay. So feasibility problems. For a feasibility problem, the problem is defined as this way. You have to find these decision variables x1 to xn. Let's say this is equal to a vector x, such that this fx greater than 0, this condition or this constraint is satisfied. The corresponding command or solver is FISB, and its syntax looks like this using that MATLAB LMI control toolbox. And this is a sample program in MATLAB which solves matrix inequality and obtain a matrix that satisfies particular these conditions using the FISB solver. See this green color text. The first one says that the constraints are given. We have to find a P matrix that is greater than identity matrix satisfying the Lyapunov inequality A transpose P plus PA greater than 0. The A matrix data is given. Then we define these inequalities here. First define the dimension of element. So this is a 2 by 2 matrix. So P is also a 2 by 2 matrix and its symmetry. So this is the syntax of defining the variables. Then define these two inequalities or whatever be the inequalities for you. For this case, These two are the inequalities. So first one, uh, first one is defined as p greater than 1, p greater than I. So this is the corresponding syntaxes, and second one is defined is using this A transpose P plus P less than 0. And then you collect all these element terms and call the solver and find a solution for the P after solving this from the set of solutions. The solution, if you run this code, then the solution looks like this, that it does an iteration and arrive at a feasible solution, and corresponding P solution is this. See that the best value of T should be negative for feasibility, so T is negative, so this is a feasible solution. So that way you can solve very easily given an LMI problem, and many control problems can be framed as an LMI problem. The main important thing about the LMIs is that it's convex optimization problems, or if constraints are as an LMI, these are convex problems, and convex problems has the benefit that if you arrive at a local solution, then that solution is the global solution itself. So you start from any point and converge to a local solution, and you will automatically get the global solution for the problem. So here also you can see this is an iterative approach and takes the solution or from a starting point and arrive at a particular minimum, right? So that's why convex problems are attractive, and solvers are also available which written already the codes for solving the problem, right? Then we'll look at how the different control problems are obtained as an LMI problem or solving LMIs. First is that the quadratic stability or the Lyapunov inequality. Particularly many robust control problems we solve using the quadratic stability or using Lyapunov's direct approach, and many of them can be expressed as LMI problem, and we can solve them very easily if a solution exists. So consider the Lyapunov's direct approach. For that, we take a nominal system x dot equal to x. Then for that we define a Lyapunov function v equal to x transpose px for linear system. This is very much standard, and we continue with this for other problems as well that involves linear systems. So v dot x equal to x transpose into pa plus a transpose p. So if you keep this p greater than 0, then this v will be always greater than 0. And if you can ensure this bracketed term as less than 0, then its derivative or derivative of v will be less than 0. So that is the basic philosophy, that you have to take a function that is always positive and you have to decay it out so that this v will decay out and will approach to 0. So once v decay out, obviously x will decay out, right, given that p is constant. So condition becomes that you have to find PA plus A transpose P is less than 0 or not, with P should be greater than 0 or a positive definite matrix. The corresponding solution can also be obtained using Lyapunov equation, that you equate A transpose P plus PA equal to minus Q. You solve this algebraically doing summation and addition, summation and multiplication, and by that you find whether you are getting a positive definite P or not for a given Q, right? So we'll continue with this inequality way, that we'll try to find a positive definite solution given these inequalities. Obviously for the uh, algebraic solution, for a chosen Q will have a particular solution. So for different choice of Q will have different P. But when you define this as inequality, so there could be several solutions of that P from that set of feasibility or the feasible solution, right? So this option remains open, that it defines a set for the feasible solution of P, right? And you can augment several other constraints by specifying the performance corresponding to a particular control objective, right? Then for robust control design, or when there are uncertainty in the system, you want to minimize something or minimize the disturbance. In such cases, we often apply the quadratic analysis or the similar way the Lyapunov's direct approach. The benefits are manifold.